Let's continue our review of the basics of integration. In this video, we will talk about some integration rules, and we will work through several foundational sorts of examples. Now on Canvas, there is an indefinite integration rules practice, which has all of the foundational, fundamental integral rules that you should have memorized. There's also a list of solutions, and I would encourage you to print out this page of practice and just work through writing the solutions here. Compare with the solutions page until you're very confident with all of these rules. Some of the rules we will use more than others, but you should have all of them memorized. But let's just highlight which of the rules are probably more typical to be seen. We'll see the power rule quite a bit. We'll see the rule for 1 over x quite often. We'll see e to the x. We will see the antiderivative of sine, cosine, and 1 over 1 plus x squared actually shows up fairly frequently. Now, all of the other rules are important as well, but these are rules that show up very frequently, so we want to make sure that we're very comfortable with them. Notice, as we look through this list of rules, that there are some rules that appear to potentially be missing. If you think of the derivative rules, we had rules such as the product rule, the quotient rule, chain rule, and those told us how to take derivatives of generic products and quotients and compositions of functions. Notice that we do not have those sorts of rules for antiderivatives. This is an important observation. Notice that there is no antiderivative rule for the generic product of two functions. There is no rule on this page for this sort of an expression. Similarly, there is no rule for the fraction of two functions. It seems to be missing. The reason why there is no rule written is because in general, there is not an integration rule for products that always works, or an integration rule for fractions that always works. There are different techniques that sometimes can be applied for products or fractions, but they're not guaranteed to always work. We can have relatively simple looking expressions where we cannot take the integral. Think of the example from the last video. We had sine of x divided by x. It's a relatively simple fraction, but there is no integral rule for fractions in general. So as we're becoming more familiar with integration and the different techniques, we want to understand this idea that some integrals we just can't integrate. We don't have rules for certain situations such as products and quotients. All right, let's practice with some foundational, fundamental sorts of integration problems. We'll work through some of these examples from this handout. Let's start with example 1. We have the integral of 1 plus x plus cosine of x dx. Now looking at our antiderivatives rules page, the integral of a constant is the constant times x. So the antiderivative of 1 is x. The antiderivative of x is x squared divided by 2. This is the power rule for antiderivatives. We have an exponent of 1 to begin with. So when we take the antiderivative, we increase the power by 1, divide by the new power. The antiderivative of cosine is positive sine of x. We tack on a plus c, and that's our answer. Whenever we're finding indefinite integrals, we can always check whether or not our answer is correct by taking the derivative. Let's do that here. This is a good idea to do for any antiderivative problem that you encounter. The derivative of the answer should be the original integrand. So we take the derivative of x plus x squared divided by 2 plus sine. We can ignore the plus c because it's a constant. The derivative of x is 1. The derivative of x squared is 2x. So we have 2x divided by 2. The derivative of sine is cosine. And if we cancel the 2's, we see that our expression is exactly what we started with. So we know that we solved this integral correctly. Let's take a look at example 2. Example 2 is a definite integral. So we will use the fundamental theorem of calculus to first find the antiderivative capital F, then plug in the upper limit 2 and then the lower limit 1 and take the difference. The square root of x can be represented as x to the 1/2, and we can once again use the power rule. Now, we see the square root of x fairly often for antiderivatives, so you want to be really comfortable with the integral of square root of x. When we have the antiderivative of x to a power, we increase the power by 1, so we have x to the 3/2, and then we divide by the new power 3/2. We will plug in the 1, plug in the 2, and take the difference. I don't like the fraction divided by the fraction expression here, so we can invert this denominator 3/2 and multiply by 2/3. So let's rewrite this as 2/3 x to the 3/2, integrating from 1 to 2. We first plug in the 2. Now we subtract, plug in the 1, and there's our answer. Let's take a look at example 3. We have the integral from e to 4 of 1 over x dx. E is the special base of the natural log function. This is 2.71 something something something, so slightly less than 3. Our first step is to find the antiderivative of 1 over x. That is natural log of the absolute value of x. This is a very, very common antiderivative in calculus 2. This is an integral that we want to be very, very confident and familiar with. So there's our antiderivative, capital F. Here are our limits of integration. We plug in the upper limit of 4, plug in the lower limit of e, and take the difference. Natural log of e is 1, so we have natural log of 4 minus 1. Let's look at example 4. We have the integral of x times x plus 1 dx. Now, notice that we have a product in the integrand. And before we work through the correct solution, I want to show you a false solution. It's a solution that might seem intuitive at first, but it's completely false. So don't even copy this down. Just watch what I write, and we'll talk about why it's incorrect. It's tempting when we see this sort of a problem to first integrate the x and then integrate the x plus 1. If we do that, integral of x is x squared divided by 2, and then the integral of the x inside the parentheses, that's again x squared divided by 2. The antiderivative of 1 is x. So it's tempting to write this as the answer. This is incorrect. The reason it's incorrect is because I am assuming that the antiderivative of a product is the product of the antiderivatives. That assumption is false. Whenever I integrate a product, I need to use some other method. I can't simply take the antiderivative of the individual factors. So this solution will not work. Let's take a look at the correct solution. The correct way to find the antiderivative is to first distribute the x into the parentheses. We have the integral of x times x is x squared plus x times 1, x. Now that we have separate terms in the integrand, we can integrate these terms separately, and we'll have our answer. The antiderivative of x squared, that's a power, so we increase the power by 1, divide by the new power. The antiderivative of x, x squared divided by 2, add plus c, and there is the correct answer. Let's look at example 5. We have the integral of 3 plus x divided by x. Now, once again, I'm going to show you a false solution which might seem intuitive at first, and we'll talk about why this is incorrect. So once again, don't write this down. We're tempted on this to first integrate the numerator, that would be 3x plus x squared divided by 2, and then integrate the denominator, that's x squared divided by 2. This is an incorrect answer. It seems relatively intuitive though. I'm taking the antiderivative of the numerator, and I'm taking the antiderivative of the denominator, and I'm combining them together. But this is incorrect. The reason is there is no integration rule for a fraction in general. I can't simply integrate the numerator and then the denominator and divide both. it gives me the wrong answer. We could check. If we took the derivative of this expression, it would not be equal to 3 plus x divided by x. So this assumption is incorrect, and this is what we want to watch out for as we become more proficient with integral problems. So what is the correct approach? Well, the correct approach is to somehow deal with that fraction before we integrate. And the way to do that is to split up the fraction at the plus sign in the numerator. We can express this as the integral of 3 divided by x plus x divided by x. I have to do this algebraic step first before I can use calculus. Now, this sort of a breaking up the fraction can only be done when we're adding or subtracting in the numerator. If we had a relatively similar looking integral, such as x divided by 3 plus x, this is not equal to the integral of x over 3 plus the integral of x over x. We cannot break up a fraction in the denominator. We can only work through this by breaking up the fraction in the numerator. All right, so once we've broken this fraction up appropriately, we can integrate. We have 3 over x, which is 3 times 1 over x. The antiderivative is 3 times the natural log of the absolute value of x. X over x is simply 1. So we're integrating 1. The antiderivative of 1 is x. Add plus c, and we have our final answer. Let's take a look at one final example. Example 6. We have the integral of 4 divided by x squared plus 1, and we are integrating from -1 to +1. This is an integration rule that we need to be familiar with. If we look at our list of rules, we'll notice that this is arctangent. Let's take out the 4 to begin with. So we'll have the integral from -1 to 1, 1 divided by x squared plus 1. And we just need to recognize that the integral of 1 divided by x squared plus 1 is arctangent. So we have 4 times the arctangent of x. We are integrating from -1 to +1, so we first input the +1. Now plug in -1, take the difference, and that is our answer. It's very important to be comfortable with the foundational integration rules as we begin Calculus 2. Make sure to memorize these, practice with them, and be familiar with using them. The x squared plus 1 in the denominator tells us that this is the derivative of... I can't talk.